Thanks, Julian. Hi, I'm Etan. As you might have guessed, New Relic collects a lot of data, and one of our greatest challenges as a company is to, and myself as a designer, is to present that data in a way that provides meaning so that our customers can make good decisions. So I'm going to talk a little bit about data viz history and different types of charts. I'm going to get into some design principles, and finally I'm going to talk more about data mining. So the first question to ask yourself is, why use a data visualization? And the reason is because human beings are really good at seeing visual patterns. So this is some kind of socio-economic data overlaid on France. And just at a glance, you can really easily see the dark region on the left corner has some significance. It's different than the sort of middle top of the country. And this taps into the human brain's ability to recognize patterns very quickly, practically at a subconscious level. And these are things like orientation, the size and shape, relative position of things, color. One of my favorite examples, in this case, DNA collected at a crime scene. Each column is actually a different DNA sample taken from the crime scene. And what's cool about this is you can really quickly glance at it and find matches between two samples, or in this case, where some of the bars are lining up and are the same size, it indicates a family relationship. So this could be brother and sister or mother-daughter. So a little data viz history. Human beings have been creating visualizations for a very long time. The earliest examples are usually geographic maps. This is one of the most popular sort of infographic style data visualizations done by someone named William Playfair in the 18th century, where he shows how imports and exports changed dramatically for a region when the political climate changed. Another example that I really like is Nurse Nightingale, who's also a statistician. She was working during the Crimean War, the British Crimean War, where she was indicating how soldiers were dying more often from preventable illnesses than they were from battle wounds. So the blue region is preventable illness, and the light red region in the middle is actual battle wound deaths. This is called a circular area chart. When designing visualizations, like many things, we follow a process for design. We acquire, parse, and filter data. We mine data, which is putting it in better mathematical context. Finally, we visualize that data, and we refine it, and we're able to interact with it. And you can see how these different parts of the process fall into different skill sets. And of course, this is an iterative process. So when you interact with a chart, you might end up refining it or further mining that data. So I'd like to talk briefly about representing or visualizing in a graphical sense. And in this example, we're looking at delicious bookmarks, and it's a network diagram of delicious bookmarks based on tags. And so there's only one thing you can really see out of this visualization, and it's that there's a central theme to this person's bookmarks. And in the periphery, there's a few other ones that really don't fit into the network. Now, this is kind of cool, but I would consider this to be more information art rather than data visualization. And this brings me to a point of, when you're trying to figure out how to visualize data, the most important thing to ask is, what problem are you trying to solve? The goal is not to provide a picture of the data. The goal is to provide meaning so that people are able to make better decisions. When making graphic design choices, one thing to keep in mind is the human brain is highly tuned to see differences, but not absolute values. So this is a really famous example where the small square at the bottom is actually the exact same color as the squares overlaid on this gradient, but your brain compares it against the background, so it's very hard to tell that they're all the same color. In a similar example, if you look at the relative size of the big lines, it looks much more different than the relative size of the little lines, despite them being actually the exact same proportional difference. And this leads me to some principles on making these choices when choosing a visualizer. In the earlier example, you saw Nurse Nightingale. She had this circular area chart. Tufte calls this the lie factor, where the visualizer you choose has this distortion effect. So for example, it's hard for me to read this close, but the circular area chart over here on the left has a distortion factor of 2.5 times compared to things when viewed as a regular bar chart. A similar example, this is showing rainfall in Tokyo. So at a glance, you might be surprised to find that in June and October, there is a huge difference in rainfall between that and, say, August and December. But in fact, this is because the y-axis wasn't scaled at 0. So when you look at it with a y-axis scaled at 0, it's a lot less exaggerated. We actually have a similar issue when we display a throughput chart on New Relic's overview screen for app monitoring. The throughput chart automatically scales its y-axis around sort of the variance within the time window. And unfortunately, this makes the chart look really interesting, but it has the effect of exaggerating kind of minute differences or fluctuations in throughput. Another important rule, a Tufty rule, is don't use don't use ink that isn't data ink or unnecessary ink. So in this case, if you look at this train schedule in France, if you just fade out the grid lines, it's immediately more easy to see kind of the important information in this visualization. Finally, another rule I like to follow is try to avoid 3D charts. This is the kind of thing Excel sometimes poops out when you put in data. And the problem with 3D is often things are obscured by data, series data behind it. So you have to be able to rotate it to kind of see it from different angles. So it's something I would avoid. And I'd also like to talk about data integrity. So in this example, we're looking at the relative size of military spending budgets of the United States compared to other countries. And what you might conclude from this is that the United States is a big military spender, an industrialized military complex. But in fact, if you re-represent this data as military spending as a percentage of the GDP of the country, we get a very different picture. In fact, Myanmar appears to be the biggest military spender as a factor of its own economy, and the USA comes in at around 8th place. And I don't mean to suggest that this is any more true than the previous visual, but you can tell there is such a dramatic difference when you represent the data a little bit differently. At New Relic, we have a lot of time series data. So this is our typical stacked area chart over time of different layers of our application server response time. And there are many other tools we can use to visualize time series data. Some of my favorites, this example is called a radar or spider graph. And what you can do is overlay multiple days worth of data in clock formation like that. And you get to see cyclical patterns that you wouldn't otherwise see in sort of a traditional line chart. This is called a cycle plot, which is actually a combination of a bar chart and a line chart within each bar. So the bar, in a sense, is the average line in each month for real estate listings. And then within each month, you see the trend of the actual month in a more detailed way. So there's a lot of data packed into this chart. Of course, box plots are also a great way to show variance around an average. So each horizontal line is an average, and then the box itself is some standard deviation around that or variance around that average. Heat maps are another really great tool, especially in this case if you're visualizing response time data in a time series. If you are intending on drawing each pixel for each hit, and what the response time was, there's a high risk of overplotting where pixels are overlaid on top of each other. So what we can do is instead darken regions using a heat map, and this is a great way to show where response time tends to be and that variance again around it. So one thing we were experimenting with was, we can visualize a heat map of average response time, but what if we wanted to focus on the asynchronous nature of activity on an application server? So imagine we have an application called recipes application. We've got 3 endpoints, one to list recipes, one to show a recipe, and one to add one. So let's imagine we have a request between 1 and 1:02 p.m. It starts at 1 o'clock, takes about 20 seconds long. And then before that request is completed, the server fulfills another one that's slightly shorter at 15 seconds long. And you can see where they overlap because of this opacity trick. There's this sort of heat map darkening effect. So if we show that for recipes list and then the other APIs for this application, you don't just get a sense of the sort of heat map of the response time for an endpoint or the whole application, but you get to see whether there's an asynchronous relationship if you look vertically. And so I tried this exercise on New Relic's data about itself. So this is activity of New Relic, our application, for about 6 minutes. And this is about 6 times real-time speed. And you can see the busiest web transactions are near the top. and the kind of quieter ones are near the bottom. And for the most part, it continues along like this until about 3/4 of the way through. And it's about to hit right about now. You'll see this effect. There it is. So it starts to get dark, and then it kind of resolves at the end. And this isn't just a slowdown, for one area of the application or the whole application. It's some things are affected by it, other things aren't. But it's really easy to tell in that column that multiple things slow down together. And you can provide more contextual information in this timeline. Below that, we could show server activity or disk I/O or memory usage. And that really will resolve certain things in your application that you wouldn't otherwise see in a regular average response time, where certain extremities of the app will, when accessed, work together to cause application slowdowns. Another time series example I really like is this animated scatter plot over time. This was borrowed from an online source. And on the y-axis, we've got life expectancy, and on the bottom axis, we have income per person, and each circle is a country. And as the animation starts, I'd like you to keep your eye on the big red ball. That's China. The size of the ball is the population of that country. And look what happens as China goes up, right about here. Do you see that? And then it starts to resolve, and everything kind of moves over to the top right. Does anyone know what happened in China in the late 1950s? So the Cultural Revolution was related, but actually it was that economic change that coincided with a environmental change that caused crop failures. And in fact, it was known as the Great Chinese Famine. In fact, estimated almost 40 million people died in that famine. It might have been one of the greatest tragedies in human history. I didn't even know about that, by the way, until I looked at that chart. Network diagrams are something we're seeing a lot more of, and at New Relic we're exploring this. This is not yet a public network diagram that we're experimenting with, showing how applications in your infrastructure are communicating with each other. And I couldn't resist putting this one in. This is the FutureStack network diagram of everyone who's connecting with each other at FutureStack. And it is so dense that it actually crashed my browser within about 10 seconds. But the problem with network diagrams is they're highly susceptible to the layout algorithm you apply to them. So in this example, these are all the same network diagram, but with different layout algorithms applied. And the problem is they look very different. And if you have a network diagram that you are kind of studying and you revisit that a day later, or the network has changed, it's very hard to notice a change in the network because the layout algorithm is such a huge influence on how it looks. And one solution around this is something called the Hive Diagram. This example is actually from the D3 gallery. And what you can kind of think of the Hive Diagram of is sort of like an aggregation of a network diagram. It's a way to provide a stable layout to a network diagram so that you can kind of compare it more easily. And you have a few variables to play with. One is the number of axes and which axis a node is on. And you can also experiment with where a node appears along an axis. So I want you to imagine, if this was application data, perhaps each axis could be which data center your application is on. So let's say the top one is the Chicago data center. This small axis is the Amazon Web Services on the East Coast. And let's say you place a node along the axis based on how high throughput that application is. And so what this means is you get the stable layout network diagram of your application environment, and you can compare it really easily when you look at it the next day, let's say, or if there's something dramatically different. And perhaps this isn't the only layout that makes sense. So you could show two side by side, one where the axes are based on the data center, and the other where the axis is based on what team is responsible for that application, or perhaps what language agent that application is on. Oh yeah, that was just showing the low throughput app near the base of it, and the high throughput apps are placed at the top. This example is called a circular IDEO plot. And if you look closely at the corner here, each of these numbers on the outside is one of the human genomes, chromosomes, sorry. And within each chromosome, there are genes where the network line comes out of them, and so they connect with other genes, and this represents genes that co-express to cause some sort of disease. And this is also another kind of stable layout of a network diagram. Correlation and scatter plots are another thing that are fairly important. And in New Relic, under one of the report areas, we have this scatter plot that shows correlation between throughput, which is the x-axis on the bottom, and response time, which is the y-axis. And what you want to see is this kind of look where there's a flat response. So as the throughput goes up on your application, the response time is fairly stable. So what you don't want to see is a diagonal upwards trend where as throughput goes up, your application gets slower and slower. And this is cool, but there are many more variables in play than just response time and throughput. And so one of the challenges is how do we visualize multidimensional data sets or high variable data sets? And one example I really like is called a crosstab display, which is basically a collection of scatter plots. In this case, we're showing 4 variables: horsepower, weight, acceleration, and displacement for cars. And so the way you read this graph is if you look vertically at the column for weight and then horizontally at displacement, the intersect of those 2 variables is a scatter plot of those 2 variables. And you can see there's a strong correlation there. If I just back this up, if you look at weight and acceleration there in the middle, that's just much less clear correlation. It looks like kind of a random scatter plot. We can also take the same data and visualize it in this thing, which is called a parallel coordinate plot. And so if I, with a mouse, you could imagine brush the top of one of the bars here, and you can see how the high cylinder engines mostly have the highest displacement engines. They're the heaviest cars, except for one, and they're all the highest horsepower cars with the best acceleration in 0 to 60 miles per hour and poor miles per gallon. So when designing visualizations, another really important tool we have is how do we mine that data? How do we put it in better mathematical context? And one thing I've been experimenting with is cluster analysis. So a simple explanation of cluster analysis is if you have a 2D scatter plot like this and you apply a clustering algorithm to it, it will programmatically determine how things break up into different groups and color them. And it's not that interesting in a 2D scatter plot like this, but you can apply clustering to really high dimensional or high variable spaces. So one thing I want to do is go through an exercise with you that I call a narrative of data exploration. So this is a tool I wrote in JavaScript that visualizes data and does does cluster analysis on it. And the objective here is to kind of explore and evaluate this tool, this algorithm, and see if we can come up with meaning in this data. So the first thing I like to do, and by the way, this is countries, so each circle is a country, and I have about 70 variables in here, but I've reduced it down to 10 in these drop-downs just to make this presentation a bit smoother. So the first thing I like to do when exploring either a data or tool I don't really understand is I'm going to do what I call a sanity check and plot 2 variables that I trust have a very strong relationship. So right now I'm plotting fertility rate and birth rate, and you can see, okay, as I'd expect, fertility and birth rate are highly correlated, and this kind of shows me that I'm gaining trust with this data. I'm going to try something that is in the news a lot lately, so to speak. I'm going to choose life expectancy on the y-axis and healthcare spending per capita on the x-axis. And you can kind of see there's a correlation here. It looks like, it's hard to see the bottom axis, but as healthcare spending increases along the bottom here, you can see this sharp rise in life expectancy, and then it kind of tapers off, and the most expensive ones, there's not much more value in life expectancy. And if you're curious about those countries on the end, that's the United States, Switzerland, Luxembourg, and Norway. Now, I was suspicious about the shape of this, so I'm going to rescale the bottom x-axis and cut out the expensive countries. And you can kind of see as I do that, the correlation starts to get less and less convincing until I get to the very cheap spending countries, and it looks much more unclear. And so because I discovered that, I decided to change the variable. And instead of healthcare spending per capita, like before, I'm going to do healthcare spending as a percentage of GDP of that country. So what we've done here is we've readjusted healthcare spending so it factors in how expensive it is to live in that country. And the correlation, again, looks much less clear to me. And if you're curious about the countries on the right, which are the ones that spend the most on healthcare as a percentage of GDP, strangely, they're the United States, Liberia, and Sierra Leone. So I'm going to change gears again and explore two new variables. I'm going to leave life expectancy on the y-axis, and on the x-axis I'm going to choose improved water source access, population access as a percentage of population access to clean water. And you can see there's a correlation. It's not quite as clean as that earlier one, but definitely in countries where there isn't good access to water, which is the bottom axis, there's a high variance in life expectancy. And then as clean water access increases, it starts to resolve to high life expectancy. So what happens if I apply clustering to this? So what I'm going to do is do some cluster analysis, and I'm going to pick, for starters, the same two variables that I'm plotting visually. So improved water source, life expectancy. And what we see here is it's clustering, and it's not very convincing to me. These look like weak clusters. And the reason is because they're bunched up right against each other. And this also happens to be one of the issues with k-means clustering, or one of the limitations of k-means, where you specify the number of clusters up front, and it will, no matter what, apply that many clusters. Now, there are more advanced algorithms where they will programmatically iterate and determine the validity of clusters and then give you the right number. But I can do that manually. If I just look at this, I can kind of see how there's this gap over here. And I have a feeling if I change this to 2 clusters, it will actually cleanly break along that gap. So I'm going to change the number of clusters to 2. And it did exactly what I expected. And this starts to look more convincing to me that we have these 2 segments, these 2 types of countries. So what I'm going to do now is, instead of clustering by the same 2 variables we're visualizing it by, I'm going to start to explore the other dimensions of data and see if we can come up with something we can build this narrative on. So one thing I discovered is, if instead of clustering by the 2 ones that we're visualizing by and choose birth rate, it's not perfect, but it almost clusters in the same way visually. That implies that the segmentations that we found in this XY plot apply also to birth rate somehow. And what I'm doing here is walking through these other dimensions and testing theories, and the point of this isn't to come up with an answer. The point of this is to programmatically come up with the right questions, and then you would follow that up with research. And so instead of birth rate, I found this other convincing way to cluster it by fertility rate, which we know is related. And look carefully there. So it isn't perfect, but it actually cleaned it up a little bit more than birth rate. So we start to build this narrative in our heads. It seems like, okay, there are countries where there's poor access to water, poor life expectancy. Let's use our imaginations. Maybe in those countries there's a lot of rural populations, and since the access to water, the clean water isn't that good, there's a high infant death or child death rate. And so since we know fertility rate is births per woman, not just births in the community, perhaps people try to give birth to really big families because there's a high mortality rate and they need enough family members to help work the land, let's say. And so the next thing I tried is number of infant deaths. And unfortunately, it breaks down. So this story doesn't follow that. So what we get is this swamping effect, where the birth rate clusters kind of swamp the whole thing for one of them, and then the other one's also dispersed. That's the pink one. And there's a lot of missing data as well. The light blue is just countries that don't have that data. And so this is kind of telling me that maybe I'm kind of going down the wrong path. But you continue to do this. This is the process. And I want you to imagine it's not me doing this. It's a machine doing this. You don't have to manually do this. You could algorithmically walk through very high-dimensional data sets like this and figure out programmatically, is this a valid cluster, and start to build this story automatically around how these variables relate to each other. So I'm clustering by contraceptive prevalence, and although there's a lot of missing data, it still kind of follows that same pattern. I tried it again with school enrollment. You could imagine probably fits this, which it does, and so on. And we don't have to just do this with country data. We could apply this to healthcare data. We could apply this to analytics. We could apply this to performance data, consumer behavior. And there's a company that's famous for doing this kind of work. They're a small shop, Ayazdi, and they work in different sectors. And what they do is this kind of approach. They do analysis on very high-dimensional data sets to come up with the right questions. In this case, they did an experiment where they were taking DNA samples from different sources and determining how they would respond either positively or negatively to different drug treatments. And this final example, again in genetics, is a three-dimensional plot of genetic data, samples taken from different individuals all over the world. And you can imagine when comparing genetic samples of people, there are thousands and thousands of variables involved in that comparison. So they take the first few variables and apply it to this three-dimensional plot. And then they've taken the rest and done a cluster analysis on that, and that's the colorization. So for starters, what we see is these samples taken from people in Ethiopia, they're very close together in that three-dimensional, the first few dimensions that are visualized here. So Ethiopians in a geographic region share a lot of genes. And you can see the same kind of thing. That's South India. All those samples are very close together. But if you look at the clustering, the colorization, you get some interesting information. For example, the light green group over there, those are Eskimos, and the Bedouin are actually over here. Even though they're so geographically separated in the first few dimensions, they seem nothing alike. When clustering on the high-dimensional data, it denotes some sort of relationship. And again, with South India and I think that's Turkey. The screen is really hard to read this close, but I know that's Turkey up there. And at New Relic, we're very good at taking huge amounts of data and providing simple visualizations to understand that data and drill downs. And now that we're not only collecting performance data, but we've got the platform project collecting data about all sorts of plugins. We have Project Rubicon, which was a demo earlier today, where we're starting to collect more sort of analytics-style data. And instead of just letting these data silos form, there's a huge opportunity here to use these sort of advanced data mining techniques to really provide deeper meaning and deeper insights so that better decisions can be made. So that's the end of my presentation. And you're welcome to ask me some questions. Instead of me on the stage doing it, though, I'll just go outside and you guys can ask me around the coffee area, or I'll be at the party and you can ask me there. Thank you.